file? Yes. Okay, so what we are going to try to do today is we are going to try, I'm going to try to share my web browser so that you can see the notes that I've typed up. And I'm going to have video on my notes here so that you can see what I'm writing at any given time. So let's see if I can share content, share Google Chrome here. Okay. So right now you should be able to see both my handwritten notes and the screen that I'm sharing here, right? If not, you should unmute and let me know. Okay, so we are coming into 2.5. How do you all feel about 2.3, 2.4 stuff?
I had a question on the long, I don't know what the word for this is, the behavior at the limit.
Okay, yeah. Yeah, long-term behavior of the...
Yeah. So he gives us an example where it's a second-degree polynomial with a constant raised to a negative power attached, and goes on to say that as x goes to infinity, the e to negative x becomes infinitesimally small, so we can basically forget it. That's fine with me. What I don't understand is why the entire function isn't dominated by the first term.
Exactly. So the first term is going to infinity in that example, isn't it?
Yeah.
I also noticed that and had an issue with it. I think that just is true, but he didn't mention it. He specifically honed in on the e to the negative x would go to 0. That's true, but I think that it's completely reasonable to say that this equation, this function, will go to infinity over time. It will be dominated by that.
Gotcha.
So yes, I think that answers your question. I think you're right, essentially.
Well, but as well as it goes to infinity, so does so let's say it's x squared plus 2x plus 1, right? Is it true that x squared dominates the function so heavily that we can just forget about all of the other terms, or?
You can say that over time, this function will behave more and more like that first term.
Okay.
Because it will eventually render every other smaller exponent just unimportant. It won't weigh enough to change it.
Yep,
and the closer you get to t equal to quote unquote infinity, as t goes to infinity, though, that will be more and more true.
Yep. Awesome. Thanks.
And there are some functions that do very different things depending on where you're taking this limit to, right? Hypothetically, we could say, what is the limit as it goes to 5 or something like that, right? We want to know what it's doing at a specific point in time. And that will not always match the limit as it goes to infinity and all of these things. So yeah, that's a good question. All right, any other questions? All right, then get started. So 2.5, in 2.2, a lot of what we're going to do today is review, which is part of why I asked. In 2.2, we learned how to approach differential equations that are separable. This is the easiest case that we know how to work with, right? We know that essentially all you need to do is sort y's to the left, sort x's to the right, and then integrate both sides. You know that this will work because everything is cleanly separated, right? You can take these integrals. Maybe the integrals themselves aren't super nice. We've seen an example of that, but it's simple enough to write an answer, right? In 2.3, we learned how to solve any linear differential equations, the ones that have standard form dy per dx plus px times y equals q of x. I know in Caleb's notes, he uses, I think, G and H here or something like that, but they're just polynomials is, well, functions of X, functions of X, right? In 2.4, we talked about how to solve exact differential equations, that is, first order differential equations that are not necessarily linear, all of which have this specific differential form, but we know how to deal with the ones specifically where this is true about m and n, because we figured out that that means that we can represent this as the differential of a two-dimensional function. Does everybody feel comfortable with that? From Calc 3, mostly. If any of you have had Calc 3 already, then this should be no big deal, especially if you've had it recently. I took it, what, 7 years ago? um, but if you've taken Calc recently, this should not be terribly surprising that this is the condition that we need, because this is talking about you want this to already be sort of the derivative with respect to x, the derivative with respect to y. And then when you take that derivative with respect to y and this derivative with respect to x, you're really saying the second derivative of this unknown f function with respect to x first and then y is equal to this second derivative of f with respect to y and then x, right? So this should all, I might have said that backward actually, y and then x, x and then y, because n is, and it doesn't matter. Anyway, I think I said that backward, but it's fine. It's the same idea. You're talking about the second derivative with respect to one variable and then the other. And setting those equal to each other means that your differential can be written in this way. Set this equal to 0. If we're trying to solve for this differential equal to 0, that means that our function has to be constant. And so when we're solving exact differential equations, we are going to first check that this is true. Second, write it in this form and sort of extract the function that we're talking about, right? And set that function equal to some c. And so if we're talking about an initial condition, then we will solve for that c at the end, right? But in order for this differential to equal 0, that function that satisfies this has to be constant. Okay, so all of this, how did we solve, and anybody can answer via the chat or out loud, how did we solve these two? How did we approach these? Well, I suppose I already gave this one away. We'd integrate, okay, but how did we approach linear differential equations? Everybody should unmute. Everybody should be typing, right? How did we approach linear differential equations?
By treating them as the outcome of the product rule.
Exactly. Aha, an integrating factor, somebody says in the chat. Yes, we need mu, right? And what did we set mu to be equal to? Or linear DEs. Mu, integrating factor. Yes, e raised to the integral of p of x with respect to x, right? So mu here is equal to e to the antiderivative. It's not the c that comes out of this will always be rendered useless. It will always cancel itself out. And so we don't have to worry about it so much. But yes, this antiderivative of, if I need to zoom this in a little bit, I can, but the antiderivative of p of x with respect to x. Okay, so what we then do is multiply this mu on all sides, right? So we get this mu times dy per dx plus mu p of x y is equal to mu times q of x. And we found that this all can be represented because of the way that mu is set up. We can write all of this as the derivative with respect to x of mu times y is equal to mu times q of x. And from here, it's just a matter, I think this is, it's not quite separable. Anyway, the way to solve this, though, is just to integrate both sides, right? With respect to x, the fundamental theorem of calculus tells us that this thing will always spit out exactly u of times y. And when we integrate this other side with respect to x, this will give us the rest of our answer, right? This is equal to this. So we know that this is how we approach linear things. But what if we don't have a differential equation that falls into any of these clean boxes, right? We're going to see two specific cases. Of course, you've already watched the lecture video, so you know what they are. But we're going to see two specific cases that with substitution fall very nicely into these boxes. So in general, we will also see that substitutions can be wildly useful. You probably already know that from calculus, right? That substitution is a great tool. So for a homogeneous differential equation, I wanted to shed some light on this because our textbook has a different definition than Professor Lee gave in his lecture. Our textbook defines this as a differential equation which, when written in differential form, like this, it satisfies that m of tx ty can factor out a t, and so can n to the same power. So there are exactly as many x's and y's in every term of m as there is in every term of n. And a good way that I have found to think about this is really just, you can intuitively talk about the total number of x's and y's as long as none of them are stuck inside some other function in the way that these are, for example. If you had something that looked like sine of y over x, or even sine of x over y, that actually will work out, right? Because when you plug in tx and ty, the t's will cancel, and you'll be left with just sine of x over y or y over x, right? So it's a little bit, sometimes this is the obvious intuitive way to think about it. Other times, an equivalent, and I think I can safely say often easier to use definition, is to say that you can represent dy per dx as a function of y over x, which is to say that you could make the replacement u equal to y over x and write this out as a separable differential equation, right? This is obviously a very specific case, but it is incredibly useful. Turning something that looks just, these can be any ugly equations, like these could be any two-dimensional formulas, right? As long as every term has this same multiplicative number of x's and y's, we can simplify this to the simplest form of differential equations that we know how to work with. And that's very, very nice.
Quick review question, sorry.
Yeah, absolutely.
What is the difference between d per dx and the partial with respect to x?
Okay, so d per dx and the partial with respect to x, that's a really good question because there's a difference. Oh, where did I set my notes? There's a difference between sorry, I have it written here. In my notes for homogeneous differential equations for this exact case. Let me see if I can move this a little bit closer to the camera. I have this note, right? What happens to dy per dx here? Well, dy per dx is equal to the derivative with respect to x of y is equal to the derivative with respect to x of xu, but this is not a partial derivative. like you see in Calc 3, right? This is an implicit derivative. And I don't have the words at the ready to quite eloquently explain why they are different. But this is because u is inherently connected to x. Essentially, that's how I could explain it at the moment. Is that u is a function of x, whereas if you're talking about a partial derivative, that's talking about the derivative of a higher function that inherently relates to multiple variables. If you, like if this were, yeah, nope, that's the best I've got right now. But I'll see if I can phrase that a little bit more eloquently and maybe include that in the written notes.
Is it fair to say that d per dx and the partial with respect to x are the same in the univariate case?
Yes, in the univariate case, they are absolutely the same thing.
Okay, awesome.
Yeah, that's a very, very good question. It's one of the things that Calc 3 touches on, but maybe doesn't, I don't know, depending on who's teaching it, especially, may not go into satisfactory detail.
It's been almost 4 years since I took Calc 3, so it's a little rusty.
Oof, yes. Yeah. No, I definitely feel it. Okay. So, let's see, move to example 1. And I would love for you all to write along with this to see if you can solve this while I'm working it through. Okay, example 1. Solve x squared plus y squared dx plus x squared minus xy dy. So the first time I worked this problem, it seemed like, first of all, Professor Lee had obviously overstated the usefulness of this function of y over x, because I could not find any way to put this in this form without doing something really weird. And so that really weird thing that I eventually figured out is what I'm going to share with you. But this definition from our textbook is just clearly true, right? This function, this differential equation, clearly can be checked that every term has 2 of these variables and they are all multiplicative. So obviously, if you took a t in with every x and a t in with every y, both m and n could factor a t squared out front, right? So that is a very intuitive answer for this problem, that this is very clearly homogeneous. Homogeneous? But this should be very clearly homogeneous. That doesn't really help us immediately, right? Because by the book's definition, it just says, like, checkbox, yes, this is homogeneous, so we're going to make this substitution of u equal to y over x. But then you're dealing with something that looks almost as ugly as you started with. And so what I would recommend doing, instead of just immediately making this substitution, is actually to follow what Professor Lee recommends. To try to put this into dy over dx equal to something written in terms of y over x. Okay? So let's get down to business. We want to subtract this one over and then divide by dx, divide by x squared minus xy, right? Okay, so we have x squared minus xy times dy is equal to x squared plus y squared dx. And then divide things over. We want to divide by dx and by this x squared minus xy. So that we can move this to the right and this to the left. Okay, so we wind up with dy per dx is equal to x squared plus y squared divided by x squared minus xy. And this is where I personally stopped and was like, what the, how am I supposed to work with this? Like, I could split this up. Okay, x squared over, factor an x out in the bottom, I guess. But that's not any nicer. I just x over 1 minus, or x over x minus y, and y squared over x squared minus xy. Like, that's no better. But what I figured out, and this is a trick that you should employ if you find yourself in this situation with a fraction sort of thing like this, what you can do is for every y, charging has stopped, the temperature is too high. Okay. But for every y that's in here, you can multiply its piece by 1 over x to balance that out. So what I wound up doing was this 1 over x squared, 1 over x squared. And what you see is then, because the bottom was factorable into x times a thing, we have this extra x, and then we have a y. Okay, so what this will equal then is x squared over x squared is 1, plus y squared over x squared is y over x, quantity squared, divided by x squared over x squared is 1, minus xy over x squared will be just y over x. And suddenly, lo and behold, we have a function in terms of y over x, right? Okay, so this is beautiful. The reason is that we can make this substitution now and actually have somewhere to go with it, right? We'll be working in just u, although this dy per dx turns into u plus x du per dx. Okay, so we'll still have some kind of x running around, but let's, at this point, make this substitution. U equal to y over x. Because this is homogeneous, we know that this definitely is the substitution that we want to make. Okay, if y is equal to, or if u is equal to y over x, then dy per dx is equal to the derivative with respect to x of y is equal to the derivative with respect to x of x times u, right? And this, like I mentioned, this is an implicit differentiation, right? This is a single variable function that happens to have the primary function relying on x wrapped up in it. So we have to talk about implicit differentiation here, not partial differentiation. So this is equal to a product rule situation, right? This is the x per dx times u, that is just x per dx times u. Do that right? Give me a second. Yes. Psyching myself out. Plus x times du per dx. This is just product rule through implicit differentiation. Okay, so dy per dx will be replaced with this. So we come out with u plus x times du per dx is equal to 1 plus u squared divided by 1 minus u. So what can we do with this? Let's see if we can separate it, right? Because what we know is that homogeneous differential equations, see, here. To solve this type of differential equation, we make precisely this substitution, reducing the complicated differential equation in terms of y of x to a separable differential equation in terms of u of x. We will always, should always come out with a separable differential equation here. Okay, so let's work on separating this. Do I want to? Yeah, I'm going to make it so that it's just du per dx over here and move the rest over. So subtract this u minus u. And I'm actually going to simplify this, right? See if I can bring this u into this formula. So this is equal to 1 plus u squared minus u times 1 minus u, right? Over 1 minus u. That is just turning this into its own fraction of the same type and then squishing them together. But what we see is that this u times 1 minus u, that is, in parentheses, u minus u squared, right? Let me see. I have something mixed up. What did I mix up? I have u minus 1, not 1 minus u. How did this happen? Give me just a second. Way back. No! Oh! Okay, give me a second. I didn't put a negative. Ah, nobody stopped me. Oh, terrible. Okay, this is supposed to be negative. I subtracted this on both sides. What? Okay, so don't just trust me at my word, right? If you are working this at the same time, you should catch these things. Okay, so this is supposed to be negative. Of course, we subtracted this to the right side at the very start. This is negative parentheses x squared plus y squared. So that this is negative parentheses this all. And in my personal work, what I did to remedy that was I changed this to y over x minus 1. Because that's equivalent, right? The negative in the numerator can just be moved down here to turn this around. Alternatively, you could have just applied it to the top and made this negative squared minus 1. Okay. So I'm going to attach this to the bottom and put in an extra parentheses here. This tracks all the way down to here, where I am going to say is equal to u minus 1, and that should fix this error. Okay, u minus 1. I was going to say, because I'm supposed to come out here with a u squared minus itself. So this should be instead u minus 1. This should be instead u squared minus u. Okay, because what this turns out to be is that these u squareds will cancel. You're subtracting this parentheses u squared minus u. Okay, so we come out with x times du per dx is equal to, we have 1 plus u squared minus u squared plus u divided by u minus 1. These will cancel, and you're left with 1 plus u over u minus 1. Then we want to multiply by 1 over x, right, to get this by itself. Okay. So we have u per dx is equal to 1 plus u over u minus 1 times 1 over x. And this is our separable equation, right? This is our g of u and h of x. This is separable. Oh God, separable. There we go. Too many P, R, B all in a row. This is a separable differential equation. And so we know how to approach this, right? For a separable equation, immediately what you want to do is take this g of u, move it to the other side, and then integrate everything with respect to x, right? Or you can talk about moving g of u to the left, dx to the right, and just integrate. Totally valid, equivalent ways of thinking of this, right? So what we want is, I am going to move this g of u to the other side. So I'm multiplying by u minus 1 over 1 plus u. Get this. U minus 1 over 1 plus u. Du for dx is equal to 1 over x. Okay, and then we see that, okay, if we integrate respect to x, integrate respect to x, then these will cancel. We come out with something going on over here that we aren't necessarily very sure about. But over here, okay, we know how to deal with this. This is just a natural log, right? So the integral of minus 1 over 1 du is equal to the natural log of the absolute value of x plus some c naught. So in this case, in the textbook, it specifically says that they use be clever enough, I suppose, to notice that this numerator is just the denominator plus a constant, right? They both have just u. And so we can rewrite this as this is equal to 1 plus u. Let's see, and the difference will be minus 1, right? 1 plus u minus 1 is just equal to u. This one. Right? So I'm imagining that I'm rewriting u as this. Okay. Minus 1 over 1 plus u. This is probably not the cleanest way to write this. But this is a really common trick in all kinds of mathematics, but especially anything calculus based. This trick of just add 1 and subtract 1 at the same time to get the sort of form that you want. Or multiply and divide at the same time. And right, we see this all the time. So this is equal to, you can split these now into 1 minus 2 over this. So that we have just a constant on top. And the reason that I am doing that is because I want to be able to write, anytime I have a fraction like this, and especially anytime that I have just a single power in the denominator, I want to be able to write this integral as a linear or as a natural log of u in some sort of fancy way. And in this case, we absolutely can. So this is equal to the integral of, parentheses, 1 minus 2 over 1 plus u. du. And this, of course, is just a natural log of 1 plus u coming out here. And a 1, okay, so we'll have to split this up. So this is equal to the integral of 1 du minus 2 times the integral of 1 over 1 plus u du. This is equal to just, this is with respect to u now, so we're coming out with just a u plus a constant that we'll factor in later, minus 2 times the natural log of the absolute value of 1 plus u, right? Plus some constant, C1, let's say. Does everybody follow there? That's a lot of, like, I don't know. It took a lot of sort of jimmying this around to find some of these little obvious things that the book skips. So we can put this back together with this up here to say that we now know that u minus 2 natural log of the absolute value of 1 plus u is equal to the natural log of the absolute value x plus some c might call it C2, I suppose. And what we want here is to get u by itself. That's always sort of our goal, right? We want to get an explicit solution in terms of u. I apologize if my camera isn't focusing very well today. I'm not sure what's up. So what we want to do is use our logarithm rules. We want to put all of these logs together and then be able to squish them into just one logarithm of a product of things. So we will add this to both sides to get u is equal to natural log of the absolute value of x plus C2. This is the other sort of trick that we're doing in that I want to just take care of in this step, is that because the range of the natural log is the entire reals, we can identify any specific constant as the natural log of some other constant greater than 0. The greater than 0 isn't terribly important to note, but it will be true, right? Okay, so we can replace this so that we can make better use of these logarithms. The natural log of c plus 2 times the natural log, the absolute value. And I'm a stickler. I always bring my absolute values along. I know that 99% of the time it won't matter at all, but I am a theoretical mathematician as opposed to an applied mathematician. And so even though I know that most of you are engineering or aerospace or things like that, that you will use these in the real world, you likely will not have any use for solutions in the negatives. But just in case, theoretical side of me is like, but what happens in the negative? So I always bring them along. Okay, but with these natural logs, okay, this 2 will come up as an exponent. And all of these natural logs will be compressed into a multiplication. Oh my goodness, I'm only going to get through one example today. That is insane. Okay, I'm going to just talk you guys through my other examples then. Taking too long. Natural log of c absolute value of x times 1 plus u squared, right? And from here, I actually want to call this like C3, frick, too many C's. C3, 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 and then be able to call this plus or minus plus or minus C3 equal to C, right? So that we can absorb that absolute value of X. So that we have U equal to this thing. And at the end of this problem, the only thing that you have to remember to do is absolutely put back your y's into this, right? Sort of take away this substitution so that this is y over x is equal to the natural log of c x times 1 plus u. God dang it. y over x squared, right? And in your book, they replace x with x squared over x so that they can distribute an x in here and turn it into a lovely c over x times x plus y quantity squared, which looks nicer, but doesn't really matter, just in case you're looking at your textbook solution to this problem. Okay, so this is an implicit solution to this differential equation. Okay, moving on back to this shared document. A Bernoulli differential equation is one that looks like a linear differential equation, except that at the very end here, instead of just having q of x, we have q of x times y to some power, right? If n is equal to 0, then it's just linear. If y is equal to 1, then it would be absorbed into this p of x. We just subtract it to the other side. But if n is greater than or equal to 2, we call this a Bernoulli differential equation. To solve this type, you might have guessed, we want to reduce it to a type that we know how to work with. We just did one that reduces down to separable. It turns out that this will reduce down to a linear differential equation, right? Given that we make the correct substitution. To solve this type, we want to make the substitution u equal to y to the 1 minus n, or to the negative n minus 1, so that we can say that its derivative is equal to just a multiple of that first term. We will always come out with this 1 minus n out front. And so you can skip a lot of steps as you're going through this problem, especially because it's a linear differential equation after this point, and we know exactly how to treat those. We know exactly what our mu has to look like. We know what our solution will have the shape of, right? Our solution will always have this shape, y equal to 1 over mu times the integral of this all, right? So we know exactly how to treat this. Okay, so don't forget to always replace the original variable y of x in your final solution. Okay, so let's just very quickly look at an example. And I have my notes on this already written. If I just pull these over. They're a bit messy, but that's okay. Okay, so to save a little bit of time, I want to solve this. So the first thing that we do is put it into standard form. Usually for a Bernoulli integral, or for a Bernoulli differential equation, you will be told explicitly that it is Bernoulli before you begin. And so almost always, regardless of that, almost always, you will want to put a differential equation into standard form first to try and get an idea of what type it is, right? In this case, we see that when you put it in standard form, it has this y squared n equal to 2 sort of Bernoulli shape, right? This is Bernoulli. So what we want to do is move this, see over here, we want to move this y to the n to the left side of this equation so that we can play with this sort of substitution of y to the negative n minus 1, right? Or in this case, y to the negative 1. So we would like to make this into some kind of linear looking thing in terms of u. And always, I wrote these notes up before I had completely typed what you can see in front of you on the document, that this will always be the case. It'll be the derivative of this times some constant that will be 1 minus n. So we want to have something linear, so let u equal y to the negative 1, then du per dx is equal to conveniently just negative 1 times the rest of what's here. So the rest of what's here is equal to negative du per dx. And we can make this replacement, multiply this over, so that we have this p of x divided by 1 minus n, right? Our original p of x here was 1 over x divided by 1 minus 2. So divided by negative 1 gives us negative 1 over x, right? And so this is all lining up with this example. We know that this is the standard form for a linear differential equation of u of x. So we need an integrating factor equal to this. And we can skip almost directly to the end if you remember the shape that this has to take, right? We know that we're multiplying throughout so that we can call the left side the derivative with respect to x of mu times u. And we know theoretically how this is all happening, right? So we can say that mu is equal to e to the integral of p of x dx. That is negative 1 over x, gives us negative natural log of x plus some constant. This constant will be irrelevant every time. We've seen that u will be equal to 1 over mu times the integral of mu times qx dx. Right? This mu is not only a constant. This will be this 1 over x at this point. In my own work, I hadn't gotten rid of that constant, so it's a little bit messy. Apologies. But writing out this solution, u will be equal to 1 over mu, so the inverse of that, times the integral of mu times this q of x. So in this case, we come out with negative x squared plus c times x. Make sure that you're not dropping that c. What was it? I think that I had missed these parentheses when I wrote it down the first time, and I wound up with just negative x squared plus c and checked the answer in the book, and it was wrong. Ah, okay, take a step back. What happened? Oh, okay, just on the last step. Okay, so u is equal to negative x squared plus cx. And we know that we had this substitution, u equal to y inverse. So our solution for y, an actual explicit solution for y, is 1 over this value of u. 1 over negative x squared plus cx. Right. Are there any questions on this or the previous, Bernoulli or homogeneous things? Because if not, I want to do one where you guys are leading me through this problem, okay? I want to go through example 3 and have you lead me through it because there are steps that should be very familiar based on previous work that I know you've done, that I know you've seen. So if you would like to unmute or message, that's totally good. Where should we start with this? What jumps out at you immediately on this? It's not one of the other two forms just blatantly immediately. This is just a general substitution problem. So what jumps out that maybe we should try substituting? Come on, unmute. Talk about it. Okay, it looks like negative 2x plus y will be a problem. Indeed, we do not want to deal with that at all. So just like when you were in Calc 1, maybe even, or Calc 2, right? The thing that looks ugliest, like this is the obvious elephant in the room. We want to get rid of this and make it something nicer. So let's at least try, right? See if we can take just this and call this u. All right, if u is equal to, I'm going to just call it y minus 2x instead. If y is equal to, or if u is equal to y minus 2x, then the derivative with respect to x of y equal to the derivative with respect to x of u plus 2x, right, is equal to du per dx plus 2 derivative of 2x with respect to x will just be 2. Okay, so this isn't bad at all, right? We're just adding a constant. Hypothetically, that shouldn't cause us any trouble. So when we rewrite this problem, we will replace dy per dx with du per dx plus 2. Replace this inside with just u. So this is equal to u squared minus 7. Okay, so we have du per dx is equal to u squared minus 9. Okay, where do we go from here? What do you see in this? Looking back at the forms that we do know how to work with, right? Which one of these forms does this fall into? In terms of u of x, of course, instead of y of x. Anybody, everybody?
Would it be a Bernoulli equation?
Oh, I could only almost hear you. What was that?
Was it a Bernoulli equation?
So it totally is not. It's neither homogeneous nor Bernoulli, right? If you look back at these separable or linear or exact things that we definitely have better tools to deal with, because we've already made our substitution. Well, that isn't to say that you shouldn't make another substitution down the line necessarily, but we have made one substitution, and in this case, that's sufficient, right? This is actually a separable equation where this is our g of u and this is our h of x, right? So we can solve this just directly using integration. So let's do so. Sort this to the other side. U squared minus 9 under 1 u is equal to the x on this side, right? Once we've sorted this out, then integrate on both sides. Okay, that's fine on the right, but on the left, this is another one of these, right? Okay, how do we deal with this? The integral of just 1 dx is just x. This is x plus some constant on the right. How do we deal with this fraction on the left?
You can
It's
factor
not a
the
natural
denominator. I don't know if that helps.
What was that?
You can factor the denominator. I don't know if that helps.
Exactly. So I'm hoping, I mean, I'm an algebraist, so of course I'm hoping, but I'm hoping that it was jumping out to you hopefully from up here, right? The moment we had this u squared minus 9 show up, you should be really antsy about like, do I need to split this? Do I need to split this? Should I be factoring this? This is a difference of squares. Should I be pulling this apart? And the answer in this case is absolutely yes. Okay, so we have a u plus 3, u minus 3 in this integral denominator. What do we do with that? How do we deal with that? This already is better than this because there should be some kind of gears turning that are saying, okay, maybe I should deal with these separately. Maybe I would rather pull this apart somehow. How do we pull this apart?
Partial decomposition.
Exactly. Right? That should be sort of comfortable or getting comfortable for us at this point, right? We know that this u plus 3, u minus 3, this is really just looking like 3 under 1. This is talking about some a over u plus 3 plus b over u minus 3, right? Where we have found a common denominator, u minus 3, u minus 3, u plus 3, u plus 3, right? This is all partial fraction decomposition is. It's just talking about factoring this so that you can pull it apart into easier to work with pieces. And in this case, you will always decrease the power of the top. And so, compared to the bottom. And so you will always come out with this sort of natural log setup at the end. Anytime that you have this, you'll come out with two pieces, both of which need a natural log integrate. Okay, so what we're looking for is 1 equal to a times u minus 3 plus b times u plus 3. So this is equal to a plus b times u plus 3 times b minus a, if you distribute this, right? Divided by the same u plus 3, u minus 3. Right. Okay, so if a plus b times u plus 3 times b minus a is equal to 1, well, this u factor had better equal 0. Because there are no u's on the left side. Okay, so a plus b definitely equals 0. So we know that a equal to negative b. Okay. The right side, this is 3b minus a, so substituting this in, we can say that 3 times 2b has to equal 1. So b had better equal 1 over 6. Sorry if that's too small to see clearly, ag. But b equaling 1 over 6 implies, due to this, that a had better equal negative 1 over 6. Okay. Partial fraction decomposition complete. We can go back to this problem. Okay,
Wait,
so
sorry.
we can replace this.
Really quick. I missed, how did you get a plus b equals 0?
Aha, okay. This, so the line of equations that I have here, this is just saying that we have 1 over u plus 3, u minus 3. Can be split up into a plus b like this, but really what we're saying is just this numerator has to be true, right? Because all of these denominators, when we multiply through like this, are equivalent. So 1 has to be equal to a times u minus 3 plus b times u plus 3. When I distribute that, I get this piece here. I want to distribute it as a sort of a polynomial in terms of u sort of look. right? We have constants, we have things that are times u, we have things that are times u squared, things that are times u cubed, like that. Putting that all together, we come out with 1 on the far left here has to be equal to a plus b times u plus 3 times b minus a. Well, if we have any non-zero value here, then we should have a u over here, right? And that comes down to the abstract algebra sort of background of this, right? U and 1 are completely different objects. They cannot intersperse. You can't add up some number of u's and get out 1, right? So
Okay. Yeah, that checks out.
if you had a variable, then it would have to be over here as well. So we come out with this a plus b has to equal 0. And that will always be true, always, always, in every variable forever. And then it's just a matter of 3 times b minus a equals 1. Okay. Just a system of 2 very simple equations. So then we can plug this back in over here to say that this integral is equal to the integral of these things, where you're just saying say a over u plus 3, b over u minus 3, right? Those are the pieces that we actually care about here. So a was negative 1/6. I'm going to say, just right out front here, times 1 over u plus 3, a big parentheses, plus 1 over 6 times u minus 3. Oh God, that was a u. Okay. Right, is equal to x plus c naught. And this is just natural logs, right? Do I have enough space to finish? No, I should go to the next page. Okay. This will just be negative 1/6 times the natural log of u plus 3 plus natural log of u minus 3, right? I wanted, dang it, I should have had a negative. Oh, just going to put my negative here. Okay. All right. Is equal to x plus c1. Keep in mind, I mean, constants, they almost never matter, but well, the constant from this from this integral will combine with c naught here. So this, we want to use our logarithm rules to say this is 1 over 6 times natural log of u minus 3 over u plus 3, still technically inside of an absolute value, is equal to x plus c1. We can move this 6 over to the other side. 6 times x plus c1, right? It's equal to 6x plus c2. Absorb it into there. Raise both sides so that we get this e to the natural log of u minus 3 over u plus 3 is equal to e raised to the 6x plus c2 is equal to c3 times e to the 6x. Right? To get rid of these absolute values, we just take c to equal plus or minus c3, and then we can throw out the absolute values. U minus 3 over u plus 3 equal to c e to the 6x. And from here, it should look very, very familiar, right? We worked a problem almost exactly like this last week. Of course, this is in terms of u, not in terms of y. So you do need to remember to put back your y once you're done. But you should come out with, see if I can just, so that I don't take up any more of your time. this u equal to 3 times 1 plus ce to the 6x over 1 minus ce to the 6x. But remember that u is equal to negative 2x plus y, so we need to make that replacement. And technically, this is a perfectly fine implicit solution. But technically, if you move the 2x over, it becomes an explicit general solution for y of x. But wait, there's more. This was an initial value problem. So we should then plug in y of 0 equals 0. So plugging all of that in, we solve to see that c has to equal negative 1. Therefore, our final particular solution in terms of y will come out to be y equals 2x plus 3 times 1 minus e to the 6x divided by 1 plus e to the 6x is our final explicit solution. All right, any questions on this whole process? Just like way back in calc, right? When you are making a substitution, it is completely valid to have a guess for something that will make your life a lot easier. So test it out, right? The only thing that you really need to test is to make sure that you can write this dy per dx in any kind of nice way, right? Kind of make sure that it's not going to unintentionally make your life a lot more difficult by making this substitution. But if it makes it any easier, it's probably worth it in differential equations because we only have a set few types of problems that we really know how to tackle. So if you can narrow it down to one of those in whatever substitution works, that will be useful to you in a big way. So trust your gut. When you see this negative 2x plus y quantity squared, maybe question whether you actually need to multiply that out and try to work with it, or because it's obviously not going to be separable at that point, or if making a simple substitution will make your life a lot easier. Okay, any other questions? All right, if there are none, then that is all.